Well, not really an artist. I mean, I can do a little bit. I can ball skull map a little bit with clay and on paper. Certainly can draw out some analytical stuff and do the stick figures like Kyle Rayner's nonsense. But when it comes to this, there's an important topological model to think about why I so heavily define it as quantum mechanics.
Your experience with things that you have seen before is inadequate, is incomplete. The behavior of things on a very tiny scale is simply different.
That was Richard.
Remember that. It's an important statement. He said that. That's important. It's the kind of thing we have fun with here in the Masons and mathematicians and Salty Dogs camp. Can'ts, absolutes, all that fun stuff comes around because you can't help but say it. You can't help but say it. I know, right?
It's Richard Feynman. He won the Nobel Prize the year after that clip was recorded for understanding the quantum physics of light and how it interacts with matter. But long before he was a famous Nobel Prize winner.
Metal smoke. See, again, people forget about this. It's an important smoker pit conversation. It's like, probably not going to want to screw around with Feynman.
As a matter of fact,
it's fundamentally wrong without that math handy, and the only way to do it. And then you might even look at him and what quantum mechanics is and superpositions at times. You can't rely on your physical experiments because they're wrong. But that was a trait universal of any experiment you were about to run.
In fact, when he was just a 20-something-year-old grad student, Feynman's first great discovery was an entirely new way of thinking about quantum mechanics, which in the 80 years since has proven essential to our modern understanding of quantum physics. It's called the path integral formulation of quantum mechanics. And once you understand it, Feynman's perspective will give you a ton of insight into the counterintuitive way that things behave.
That one killed me. My brain literally was like, what are you doing, T1? That's still up and right, but maybe there's a difference about the snowflake, the marshmallow, the snowflake, and the rabbit. That, my fire flower I usually give you in a mass shell. This path integral, this up and right by weeklies, dailies, portions of the particle slit particle simulator slit experiment has negative results. It has spin, it had momentum, but it had so much spin momentum as a particle or a day in that stone mill that technically from this Laplacian point or Gaussian or in the pipes, the tubes, the Smith chart over here, that there's a path integral for that. Once that starts with that element.
Behave in the quantum world. And at the same time, it will teach you how the laws of classical physics, like F equals ma, are derived from the more fundamental quantum mechanical description of nature. Quantum mechanics is all about describing the behavior of really tiny particles, like electrons. And to give you an idea of just how different it is from classical physics,
let's instead change that measuring stick. First things first. The difference of classical mechanics and this is how we are generally taught about it. The technical truth of the matter is this baseball is 0 degree diffraction STEM microscope stuff. Yeah. Okay, what do I mean by that? Well, you can have 3 angles in Enola Gay. Your full speed, any bank of a turn, but you're going to correlate that to the full bank on the turn. Right? If you change the plane because of mathematics, X or Y, the weight of the bomb, the weight after the release of the bomb, but that's gonna, at that point, you only get those 2 things. So, all right, just cliff note, dog, you're in that. Now, change this atom to where the baseball is, and what is in there is an electron. You know what else is in there? Quarks, leptons, and a few other things. We know it because of this gold slit piece of paper right here, Fx. And what happens is all those little tiny ones in a particle accelerator or particle simulator designs, water fluid simulator, space, smoke, heat equations, are deriving sectors. It's more of a linear, one-dimensional, two-dimensional, x to y, x to y, a to b. Is your general system. But because of that existing, you need this C, this triple body problem aspect in X, Y, or Z, because there's lots of atoms and there's different compositions between them to make up the full baseball. Technically, that rule is still happening. Feynman doing the two sticks or anybody else doing the two sticks here classically or subatomically, well, I mean, for what it is, I would be classically wrong to take these numbers, but I would be classically right to apply them to this. There may be different forms. I would imagine the bones of it at least cover the lines that might have segmenta differences between what happens here. There would need to be a few, at least 3 or 4 different compositions in there. But that doesn't mean it's going to knuckle difference. In metal smoke, if you change this to the weight of a baseball, a metal baseball, just a casted metal base, perfectly smooth, frictionless, epsilon equal or less than 0, for the moment of this, because it's not going to knuckle so much, and until that variable comes up, and we would still have to make the baseball pitcher's shoulder Feynman so consistent that it doesn't wear out in a 8-hour class. Any rate, now let's go the other way. Baseball is actually 0 in the middle. Subatomic would be atomic to subatomic is to classical gravities, Earth, the planets, stars. When binary stars are operating around a star, they do field similar systems. You light this on fire, particle, smoke. You light that on baseball, metal baseball. They're still going to FMA, but with a metal baseball is going to be heavier, so you're not going to be able to throw it as more. So there's the numbers, but the same shoulder, same height on the distance away from what you're doing to the curvature. The path integral process. In there, you'll see the charts, and that's the time that they're expressing. And then there's the baseball coaches, the catcher, the ump, and the baseball player in the pipes as far as a baseball pitcher. If I can get a pitching machine to do that, because I'm breaking down the quantum mechanics and consistently doing it without feeding it, watering it, and just providing it with electricity, which is, again, another Klein bottle. But eventually that gets out to black holes. If there was a way to orbital an object around there and pick up on the tidal force, that there's every time that there's a planet comes around, it comes around this way and covers 3/4 of it, the arc sign, then, we use the initial momentum of an object, a bar that big, flywheel with bearings, if you can do it. Eventually that curvature of the piece of metal is going to cause a friction or a tilt point inside there. And little things like that are epsilon equal or less than 0 in that class. We can't necessarily use the board factory's quarks or people's quarks inside here, but you would apply to the nucleus of the company in 4 metrics, or 4 pi, 2 pi, 4, 8, 8 pi goose stuff, that those equations aren't exactly right, but what they do is provide me some of the framework. I'm saying that that's high and low, we're breaking it into the bits, that bit has a symbol to the letter, and therefore it'll go downrange. It'll still only go downrange as far as the simulator of sandbox, right? The simulation doesn't necessarily meet the criteria of blending general relativity and quantum mechanics. See, again, technically they haven't changed, and relatively they haven't changed. And so, people are getting a little bit better than that because of the timeline of Feynman. Remember, the probability of things...
Miss Nobel Prize winner?
The probability of things is him here. I don't know what the calculus was at the time for people that can understand IH derivative squared over derivative x greater than whatever. I forget exactly Schrödinger here. B equals mc squared here. We're talking about a chemical energy. We're not talking, that would still be E in that form, but in the imcurrent value of that what we're quantifying is relative to energy. There's a social field. There's the pyramids, the post office, and they require certain things. Energy, light bill is only a portion of what that is.
As a matter of fact.
And so any classical understanding that I had of that post office is correct, but it's not the same board factor number. I couldn't just rely on elements of the periodic table or something. Well, that's because teachers don't really give you, we are here to do this plasticity steel beam, and we're doing some of the discrete distribution calc as a cognitive decoherence experiment in the classroom. Now, that was a fun, fancy bunch of words I just threw down on the packy at you. It's still a Stanford experiment. It's still Milgram's enlarge in the sense, not just to the student, but also the teacher. If you don't discipline the right student, then what you're saying is you didn't quite have the correct understanding classically about that. Doing the best you can, trying to keep it on the farm and be all right with it, I guess.